Flutube. Get it straight.
Okay, let's look at one last example from the first part of chapter 4, and we're looking at velocity fields and acceleration fields here. So in this example, we have two-dimensional velocity. We've got a u component, x direction, b component in the y direction. We want to know the streamlines. Remember, the streamlines basically map out the velocity field. We also want to know the acceleration field in this case. So let's do the streamlines first. So remember, the key relationship about streamlines is that y dx, or the slope of the streamlines, is always equal to the ratio of the y velocity over the x velocity component. So in this case, that's simply equal to negative y over x. That comes straight from the definition of the two velocity components. So if we rearrange that, we get dy dx over dy over y is equal to negative dx over x. So we integrate this, we get a couple of unnatural logs. Don't forget the constant integration. So we can do some algebra, and with some knowledge of logarithm rules, we can get ourselves down to this point where we have x times y is equal to a constant. So we got these hyperbola type curves in each quadrant. Notice that I've placed some arrows on these curves. So how do we get these arrows? So in order to get these arrows, we have to go back to the original definitions of u and v, which remember are up here. Then we simply plug in some numbers there. For example, we plugged in 1, 1 for the first quadrant, we would get a positive number for u and a negative number for v. Positive and negative means that we're going down for v for x. So in other words, we're going this way. Similarly, in the second quadrant, we put in a negative number for x. We'll give a negative number here. And if we put in a positive number for y, we'll get a negative number as well. So we have negative and negative. In this case, we have x going in the negative direction. We have y going in the negative direction. So we have vectors that are going this way. So we could work our way around the quadrants doing these plugins, and we get the arrows that show the streamlines. Okay, now let's look at the acceleration part of the problem. So remember, in acceleration, we've got two-dimensional here. So we've got the local acceleration, and then we've got the convective acceleration with respect to x and with respect to y. So we have to work these out. So first of all, the local acceleration is the derivative of the acceleration, or the velocity with respect to t. So that's 0. We have steady flow, that's stated in the problem. The convective values are not 0 in the case of u. We have a u dx, so we work out the derivative. So here's u, here's du dx. Together we get these constants squared times x. Now v times du dy is in fact 0 because d dy of u, which is the constant times x, is equal to 0. To remember to do it for the y component too, because we have a two-dimensional flow here. Again, dv dt is equal to 0. In this case, dv dx is equal to 0, so this term becomes 0. The last term, v times dv dy, is not equal to 0. It has a term similar to the x term before, only it's the constant squared times y. So we have the ax term and the ay term. Use some knowledge of our vectors here, some vector math. Know that the magnitude of this is the square root of the sum of the squares. That comes out to be this term. It's a little trickier than before the velocity. And we can take one of the velocity curves here. So just grab one, here's the velocity curve. Just pick some points on that curve, and you would be able to see the magnitude of that acceleration, but also you need to find the angle with respect to the horizontal. So as with the velocity, the angle of the horizontal is the ratio of the y component of the acceleration to the x component of the acceleration. And that becomes y over x on your plot. You get these vectors that are not always intuitive compared to the velocity. In this case, let's go back to the previous plot. More clear. You can see that as this velocity, as this particle of water is moving down the corner, it starts to decelerate or accelerate back in this direction because it's got to slow down to make this turn. And as it gets down here towards the bottom, it'll start accelerating again until it's moving off in this direction again. So if you look at the plot on the next page, you start to see these acceleration vectors going first upward and inward as you make the turn. You feel this centripetal acceleration as you move in, eventually beginning to turn off in this direction. So that's the end of this problem.